I'd like to look at section 8.2 in the practice of statistics, 5th edition, estimating a population proportion. Very briefly, things that we'll do in this section include stating and checking the 10% rule, randomness, large counts condition, finding critical values, constructing and interpreting confidence intervals, and determining sample sizes. You will, of course, know all these things when you finish the unit, but that's an idea of what's to come. Now, we won't actually do this activity, but I want you to see what the rest of the presentation is talking about. So in this, you're going to have a bucket full of beads that are different colors. You're going to take an SRS from the bucket. You're going to estimate a proportion of the certain color beads, the red beads from the bucket, and then find a confidence interval around your estimate. Finally, you'll compare the results to others in the class, so that'll give you an idea of kind of where we're headed with this. Now suppose that one SRS of beads results in 107 red beads, 144 beads of some other color. Okay, so I add those together, 107 plus 144 gives me 251 beads. 107 of those are red, gives me a p-hat, an estimate for the true proportion of red beads is 0.426. Now, of course, I could dump out the beads on the desk and actually count all of them as though I know the whole population, but of course in real life you usually don't. So we'll continue to go with that assumption that we don't know the right answer, but I suspect, since this was an SRS, that the right answer is something close to 42.6%. Approximately 42.6% of the beads are red. Now, how can I use this to find a confidence interval? Well, we know we need the data to be random, and it says it's an SRS, so I'm in good shape there. We also talked about needing a large enough sample size. If I have a large enough sample size, then I end up with an approximately normal sampling distribution. If I have a large enough sample size, that means NP is bigger than 10, and N times 1 minus P is bigger than 10. I know that the middle of my sampling distribution of p-hat is the truth because it's an unbiased estimator, because it's an SRS. That doesn't mean that my p-hat is the same as p. It means if I graph lots and lots and lots and lots of p-hats taken in the same method, the center of that graph is the true p. And the standard deviation is going to be the square root of p times 1 minus p over n. Square root of p times 1 minus p over n. So there's what the graph looks like. Now, of course, the difficulty here is that we don't know p. Because if we knew p, we wouldn't bother finding an interval for where we thought p might be. We'd just say, here it is. So in practice, instead of using p, we'll use p-hat. And if I've taken a big enough sample, and if it's an SRS, then I'm pretty confident that the truth is going to be something pretty close to what I get, and that's good enough to go from there. Now, before I make a confidence interval, we want to look at these conditions. So first of all, the random. This is looking at what we just said in a little more detail. We want the data to be from a random experiment or a random sample. In this case of the beads, we're looking at a random sample. Ideally, I've sampled less than 10% of the population. I've sampled less than 10% of the population. We talked about that rule before. 10 times little n needs to be less than big N. This is written similarly, but you get the idea for that. And I need to have at least 10 successes and 10 failures. This is the number of successes. This is the number of failures. And it needs to be at least 10. This is the number of successes because it's how many times I tried multiplied by the proportion of successes that I get. So if I tried 50 times and and 20% of the times I win, 50 times 0.2 would be 10. Now, constructing a confidence interval for proportions is identical to constructing a confidence interval for anything else. It's the formula, the statistic, plus or minus a critical value, times the standard deviation of the statistic. Now the statistic for this problem is P. What we're looking for is P. The standard deviation is going to be the square root of P times 1 minus P over N. But again, we don't know P, so we use the next best thing, something called the standard error, which is the square root of P hat times 1 minus P hat over N. Now, like all videos, you're watching this, it may go faster than you're ready to take it in. You can pause it at any time or go back and watch it, but some of this is just getting the big idea and following my logic so that when I get to the end and tell you how to work it, it all makes sense and it's all logical and stepwise in your brain. The standard deviation of a statistic is called the standard error of that statistic. So how do we find the critical value? Well, the critical value comes from, in our case now, the pink chart or the normal chart or the table of normal distributions. In order to use the table of normal distribution, I need to make sure that the data comes from a normal distribution. The data will come from a normal distribution if I've taken a large enough sample size, which is what we talked about with this. The sample size being big enough to get at least 10. If I've done that, then I end up with a distribution that looks like this. And if I wanted, say, a 95% confidence interval, we've been using 2. Now, using table A or the table of standard normal distributions or my calculator, I can get a more accurate critical value by using the method explained here. If this is 95%, then 5% is in the blue region. Half of 5% is over here, half of 5% over here. I could then look up 0.025 in the middle of the chart, work my way out to see that it's negative 1.96. If you add these up, you get 0.975. If I look up 0.975 on the chart, I get 1.96. Now the critical value is the positive number there. So even if I just looked this one up, just strip it of the negative, and that's the critical value, 1.96. So we can practice a little bit. For an 80% confidence interval, if I've taken a large enough sample size to where I have 10 successes and 10 failures, I'll make me a little table. This is 80%. 10% here, 10% here. Look up 0.1 on the table, and I get, let's see, 0.1 is really close to this number. So it's close to negative 1.28. It's kind of between those two, but it's closest to that one. So my z is negative 1.28, which means my z star, the magic number that works for 80% intervals, is 1.28. It's probably worth your time to make sure you know how to do that for some other values as well, just to make sure you have the process figured out. Now, once we have the z star critical value, we know all the components. It's just a matter of plugging them in and making sure that it works. So here's sort of a technical book-like way of writing this down. Once the conditions are met, a C% confidence interval for the unknown proportion P is P hat plus or minus Z star times the square root of P hat times 1 minus P hat over N, where Z star is the critical value taken from the standard normal table, with C% of the area between negative Z star and Z star. So that's the way I'm going to find the formula, provided that those conditions are met. This is called the one sample Z interval for a population proportion. Now that seems like a mouthful, but it shouldn't be all that difficult. It's a one sample because I only took one sample. I'm using a Z star critical value, which is all you know right now, but I'll teach you some more down the line. And we're doing a proportion problem, so this is for a population proportion. What we did in the previous section was one sample Z intervals for a population mean. So suppose we took an SRS, this is back to the original question, and got 107 red beads, 144 beads of a different color, white beads in this case, and we want to come up with a 90% interval. I've made the claim that half the beads are red. So I take a sample proportion to get this, and we check the conditions that we said in just a second ago. So for a 90% confidence interval, pause the video, find the Z-star critical value that goes with a 90% interval. Using the chart, we've made a graph on a 90% interval. I've got 90% in the middle, 5% on either edge. So my 5% is in between these two numbers. If you're using the table, you'll pick the one that comes closest. In this case, they are the same, so just pick one. If you're using your calculator to use the inverse norm function, you'll see that the Z-star critical value is 1.645. Now, some of you will say, Coach, that's right between these two numbers. So why didn't we just pick 1.645 off of this? Well, it doesn't always work that way. So if you're using the chart, just pick one of them or pick the one that's closest if there's one that's closer. If you're using the calculator, you can take it to a few more decimals. So now I want to plug the numbers into the formula. There's my formula. And P hat is going to be this number right here. Now, as you write these numbers into the formula, you can either write this or you can write this. I don't care. As I'm doing it, I'd probably write 107 over 251 because I haven't picked up my calculator yet to figure this out, but it doesn't matter to me either way. So here we wrote 4.426 plus or minus the critical value, 1.645, times the square root of P hat times 1 minus P hat over N. And you could either write the answer like this or like this. I personally prefer the bottom one, but a lot of times you'll see this. This 0.051 is called the margin of error. This 1.645 is the critical value, or the Z-star critical value, and the square root of all this stuff is called the standard error. Now, if you're doing this as a problem, of course, you've got the conditions checked and you've drawn a picture as well. Now we want to interpret it. So the cookie cutter sentence says I'm 90% confident the true proportion of red beads in this container is between 0.375 and 0.477. Here's another way to say it. I'm 90% confident that this interval between 0.375 and 0.477 captures the true proportion of red beads in the container. Don't need to say mean in here because it's a proportion problem. Now remember, I claimed that there were 50% red. What do you think about my claim? Well, you don't believe it. It's possible because you're not guaranteed to be right. In fact, if we use this method in lots of different groups around the classroom, 90% of the groups will capture the truth. 10% of the groups will miss it. Which one are you in? Well, who knows? Even when you do everything right, 10% of the time you get unlucky and don't catch the truth. Nevertheless, if you're pretty sure the right answer is in here, then you're pretty sure 0.5 isn't the right answer, and you would have reason to doubt the claim that I made that it was 50-50. So let's talk about this with the four-step process and how we would go through and apply that to this problem. State the problem. Well, the problem is we've got to figure out which parameter we're trying to estimate, whether it's a proportion problem or a means problem, and what confidence level we're looking at, 90%, 95%, whatever it is. When I plan, I've got to identify how I'm going to do this problem and check the conditions. Do it. If the conditions are met, perform the calculations. Now, I would say even if the conditions aren't met, go ahead and perform the calculations and throw in the caveat that you're not real sure about this because some conditions weren't met. And finally, interpret your interval in context of the problem. Don't forget to put it in context of the problem. That's important. The next part involves choosing a sample size. So how big of a sample do I need to get to give me what I need? Well, we may want to choose a sample size that allows us to estimate the population proportion within a given margin of error. The margin of error in the confidence interval is that second part. They list it as ME here. Frequently, you'll just see it listed as M for the margin of error, which is Z star times the square root of P hat times 1 minus P hat over N, where Z star is the standard normal critical value. Now, what does that mean? Well, it means if I want my interval to be a certain size, then I need to take my sample as such. So if I want a really, really small interval, then I need to take a really, really large sample. Because remember, the larger the sample, the more sure I am about where the truth would be. So if I want my intervals to be a certain size, then I take a certain sample size to allow that to happen. Because the margin of error involves, now the margin of error, this part, involves P hat, I have to do a little bit of guesswork here. So there's two ways to do guesswork. Because remember, I can't find the margin of error until I have P hat, but I haven't had P hat because I haven't done the problem. And I haven't done the problem because I don't know what sample size to take, because I'm waiting to figure out what sample size to take so I get the margin of error the way I want it. So it's this circular argument. So I have to kind of guess somewhere along the line. And there's two primary ways to guess. The first way is to make up some guess for P hat based on what I did before, last week, yesterday, some other problem. Here's a pretty good idea of what P hat is. Let's go there. The second way to do it is to just go into a worst case scenario, and as it turns out, the margin of error is as wide as it can be for a particular context if P hat is 0.5. So I can put myself in the worst case scenario by making P hat 0.5 and going from there. Now, if P hat is anywhere between 0.3 and 0.5, sorry, 0.3 and 0.7, it's probably a good idea to go here with the 50% idea. Otherwise, when I get a little bit more extreme answer, less than 30% or more than 70%, I might be better off using a different P hat from a previous study. This will become more clear to you as I start working some questions and show you how the application fits. So from the text box, calculating a confidence interval to determine the sample size N that gives a certain confidence level for a population proportion with the biggest margin of error, we're going to solve that inequality for N, where P hat is some guess, and maybe I use 0.5. All right, you're like, Coach, I don't know what you're talking about. Let me show you, and then if you want to go back and look at this slide, you can rewind the video and get it. So here's the scenario. A company has received complaints about the customer service. The managers want to hire a consultant to carry out a survey. But before they contact the consultant, the company president wants some idea of how big the sample size is going to be so she knows how much she's going to have to pay. One critical question is the degree of satisfaction with the company's customer service, which is going to be measured on a 5-point scale. The company president wants to know if you were satisfied or very satisfied. Otherwise, they've got some issues, and she would like it to be within 3 percentage points at the 95% confidence interval. In other words, I want to be 95% confident that the true proportion of people who really like them is between this and this, and we want this and this to have a margin of error of 3 percentage points. So how big of a sample do I need? Perhaps jot this sentence down right here. An estimate within 0.03 at a 95% confidence, because that's going to be the key that we need on this next slide. The sample size needed to get a P within 0.03 with 95% confidence. Now, first of all, if I go with 95% confidence, what's the Z star? It's 1.96. Some of you guys are still using 2. There's nothing necessarily wrong with that. I mean, I guess it is wrong. It's a little bit off. But let's go ahead and use 1.96 now because we have the idea of how it works instead of just using the 68, 95, 99, 7 rule. All right, what proportion of customers are satisfied or very satisfied? Well, I have no idea because I haven't done the survey yet. So maybe I'll go ahead and use 50-50. 0.5 is going to be my guess for p hat. Now, sometimes, since we're sort of making up this p hat, sometimes you'll see it written as p star because it's a guess that I just made up. Why 50-50? Because I have no idea what else to do, so I'm going to put it in the worst case scenario, which for these problems, as you'll see later, is a 50-50 split. And by 50-50, I mean 50% of the people said yes, satisfied or very satisfied, and 50% of the people said no, which in this case confuses a few of you, so let me back up. This is a 5-point scale, but 4s and 5s are satisfied or very satisfied. So I'm taking a 5-point scale and making it a 2-point scale. If they said a 4 or 5, they said satisfied or very satisfied, they're a yes. Otherwise, they're a no. And because we want the margin of error to be no more than 0.03, I want the margin of error to be less than 0.03. So I'm going to take that equation right there and plug in the things that I know. Now, the margin of error is all the stuff after the plus or minus. It's the z star times the square root of p hat times 1 minus p hat over n. So I want z star times the square root of p hat times 1 minus p hat over n to be less than 0.03. Now, over here, you notice we said less than 0.03. Probably we should have a less than or equal to right here. But you'll see how this plays out in a minute. It's rare that that sign is going to actually make a difference. So you notice a little bit of discrepancy right there. Okay, so I'm replacing that p hat with 0.5, moving my square root of n over, moving my 0.03 over. This is just some algebra work right here. I personally would probably solve this question a little differently. If you look back at the first step, I might divide both sides by 1.96 and then square each side and go from there. It doesn't matter to me how you work it. I'd encourage you to pause this and take this equation and make sure you can solve it for this. Okay, if 1,067.111 customers would give me a margin of error of less than or equal to 0.03, then I've got to take this number and actually get a little bit bigger because I can't measure a 0.111 of a person. So I'm going to change this number right here to 1,068. If I take 1,068 respondents, I'm going to get a margin of error that's a little bit less than 0.03, meeting the threshold that the company president wants. If she decides at this point that this is way too many people to call, then she has two options. She can have less confidence, or she can allow a wider interval or a larger margin of error. Now, it also turns out that she may decide the answer is not close to 50-50. Most of our customers are satisfied. It may be more like 80-20. As an exercise, rework this problem for 80-20. If you use an 80% success rate, sorry, 20% failure rate, and work that out, you'll see the answer, the rounded answer is, I think it's 683. 683 is quite a bit less than this. But if the answer is actually 50-50, I'm going to need this. So you have to decide if what you think is a reasonable guess right there. Now that's section 2, sort of in a hurry. But here's what we did. We went through the conditions, the 10% rule. 10 times little n needs to be less than big N. I can't sample more than 10% of the population. We talked about random selection still being a crucial issue, and large counts. That means NP is bigger than 10, or N1 minus P, and N times 1 minus P is bigger than 10. In other words, at least 10 successes and 10 failures. We determined critical values, Z stars, again, just as we did in the previous section, using either the table or the calculator. We came up with the formula for finding the intervals and interpreting those intervals. We discussed the fact within this that we don't know P. So for these problems, when it uses P, I have to replace that with P hat. And we determined the sample size. We did an example to figure out the sample size needed to get a certain percent confidence with a certain margin of error. Combine this with your homework, and this should give you a pretty good understanding of Section 2.